Hi guys, we are in chapter 10. We're looking at section 3, and today we're going to talk about arcs and chords. So, let's get started straight up. We don't have any real vocabulary. So here's what we have for theorem 10.2. In the same circle or in congruent circles, two minor arcs are congruent if and only if their corresponding chords are congruent. Okay, so we're using the relationship between arcs and chords in a way that we haven't in the past. So if you notice, here's chord FG. Remember, chord is a connecting or a segment that connects 2 points on a circle. And we have chord JH. If these two chords within the same circle or congruent circles are equal in length, if I know that this length and this length is the same, then what this theorem is telling me is that this arc here and this arc here will also be of same length. Actually, I think that they're telling me it in the opposite direction. But the fact that it says if and only if, it means I can use it in both directions. So let me explain what I'm saying. So if I start off with two arcs that are equivalent, then these segments are congruent. If I started with these two segments or chords that are congruent, then these two arcs are congruent. That's what the if and only if statement is telling me. It can go either way. All right, so with that, let me go back up. With that, let me get to our first example. So we're looking at an embroidery hoop, and we are given that these two segments, AB and CD, are congruent. And basically we're told that the measure of arc AB is 60 degrees. Then what do we know about the measure of arc CD? Well, remember where the measures come from. The measure comes from the fact that we have this central angle here, so that's saying that this central angle will be 60. And what will this one be? Well, from our last theorem, we know easily that arc CD has to be 60 degrees as well. The measure of arc CD has to be 60 degrees since these two segments, the chords, are congruent. So here in example 2, we're looking at circle J, which is this guy over here, in circle K, and we're given the fact that these two are congruent and the fact that these arcs are congruent. So let's point out that this symbol means that their arc lengths are congruent, which really means that their arc measures are congruent too. But I just wanted to point it out. Okay, so we're supposed to find PQ. Well, we know from our theorem that given the fact that these arcs are congruent, then MN has to be congruent to PQ. And that means that if MN has a length of 2x plus 1 and PQ has a length of 3x minus 7, I can create a pretty straightforward algebraic equation setting both of these expressions equal to one another. With that, I'm going to solve it like I know. Subtract 2x on both sides, and then I'm given that x is equal to, I'm going to add 7 to both sides too. I'm being a little sloppy, my chablitos. But x is equal to 8. X being equal to 8 gives me the power to figure out what the value of PQ is. So notice I'm using this expression and the value of x to substitute in and get 24 minus 7, which is going to be 17. So PQ is equal to 17 units, whatever they are, inches, chickens. Anyway, let's keep moving. So we've got these theorems. Theorem 10.3 starts off and tells us, let me erase my little doodle over here. It tells us if a diameter or radius of a circle is perpendicular to a chord, as we have here, you could say that CB is perpendicular to this chord XY, or AB, the diameter AB is perpendicular to the chord XY. If we have that situation, then it, the diameter or radius in this case, is going to bisect the arc. It's going to cut this arc into two equal parts. So this guy and this guy are the same. Let's take a look at 10.4. The perpendicular bisector of a chord is a diameter or a radius. So if I have a chord, this chord XY, and I've given that it is cut in half by this segment or this segment here, I know that these segments have to be the diameter or the radius. That's a little subtle. I'm going to repeat it again. Given a chord XY and the fact that some segment is coming here and it's a perpendicular bisector, then I know that this segment must belong to the radius or the diameter. Does that kind of make sense? All right, let's take this new information and see how we can apply it. Here in example 3, we're talking about this circle here, circle S, and we're looking at the measure of the arc PQR. PQR is here, and we are given that that's 98 degrees. So I'm going to just put a little 98 here. And it also tells me that this central angle here would also be 98 degrees. Let's just hold on to that for a moment. We're supposed to find the measure of arc PQ. So the measure of arc PQ is going to have the same relationship that we discussed earlier, where we know that these two measures have to be the same, right? And that's because we can see that the radius is perpendicular to the arc, right? It's perpendicular to the not to the arc, babies, but to the chord here. And by it being perpendicular to the chord, we know that it's going to bisect it. And so if it's bisecting that, then we can be assured that it's going to cut this measure in half. And since this measure is 98, we know that the measure of arc PQ has to be 1/2 the measure of arc, what did we say, PR. And since that's 98, half of 98 is 49. So we know that the measure of arc PQ is 49. Cool? All right. Let's go ahead and see what other lovely examples we have. Here's one. We're looking at this beautiful stained glass piece, and the stained glass window has a diameter of 30 inches, and a chord from here to here is 22 inches, and we're supposed to find JL. We've got to find this length here. So here's a nice diagram that we can use of the situation. And I want to make this nice and big so we can, all right, using this diagram, let's make it a little bit larger so it's larger. And so what we know is that the diameter, GH, is going to be 30, which lets me know that the radius is 15, right? If the diameter is 30, then the radius is 15. So from here to here is 15 as well. And then this segment from here to here, I'm going to erase that 15 at the bottom because it's in my way. This radius, not radius, this chord from K to M is 22. So this is 11 and this is 11. So the question of how to find JL, where's JL? JL, that's this little piece here that I'll highlight in green, is a tricky one. Like, how are you going to find that? We've gotten that this is 11, this is 11, this is 15, this is 15. What to do? But as you continue to look, I don't know if you guys see it, because it took me a second to see it. If the radius, if this whole thing is 30 and the radius here is 15, then this radius is 15 as well. Right? And if that's 15 and this is 11 and I need to find L, I am totally keying into the fact that I've got a beautiful right triangle here. And this right triangle is going to require me to use some old information, but I'm not too worried about that. Pythagorean theorem, right? So Pythagorean theorem says that if I have two parts or two sides of a right triangle, I can always find the third, and this one would be JL. So we know that that's a squared plus b squared equals c squared. A could be the part that we're looking for, so let's just leave it as a squared, plus b squared, which is 11 squared, is equal to c squared, which is 15. So with a little bit of work, 121 is 11 squared and 15 squared is 225. I can calculate the value of a squared, or at least approximate the value of a squared, 40104. So a squared is equal to 104. Therefore, a is equal to the square root of 104, which is going to be really, really close to 10. I'll use a calculator to confirm. I'm getting 10.19 or approximately 10.2. And so that would be the measure of JL, which was kind of a funky problem. That was kind of cool. 10.2. I don't know about you, but I like problems that make me think a little bit. Nobody? Anybody? Anybody thinking? All right, let's try the next one. All right, so here we are with a new theorem. Let me make that so we can see it. So here's our situation. It says in the same circle or in congruent circles, if you have two chords that are congruent, or two chords are congruent if and only if they're equidistant from the center. So this is kind of a nice, two-way situation. FG and JH are only equal if I can prove that their distance from the center, or these segments here, are the same. Okay, so given that, let's see if we can apply that theorem to this next problem. So we've got chords that are equidistant from the center here. In circle A, that's the one we're looking at here, WX and XY both have the length of 22. We are supposed to find the value of AB. And AB, let's see, is this segment right here. So we've got to find that segment. Well, what the formula just told us, if we've got two chords that are equivalent, then we know their distances have to be the same. So this really works out pretty nicely for us, because if AB is equivalent to AC, then 5x is equivalent to 3x plus 4. If I solve this, moving the 3x over to the other side, I get 2x is equal to 4, and I get that x equals 2 by dividing both sides by 2. Obviously, we haven't found AB. We've got to substitute it in there. Somebody is not happy. Shh. 5 times 2 is equal to 10. And that's me simply replacing the 2 with the value we got for x with the value we got for 2 for, you know what I'm saying. Blah. All right, so then finally we get that AB is equal to 10. And that's about it for us, and that's about it for this particular assignment. I am hoping that this makes sense. Let me know if there's any questions with the assignment or with anything, and I look forward to talking to you guys soon. Look, this is like the first video in a long time that's just been one part. Yay, revel in it. All right, I'll talk to you guys later. Bye-bye.